My name's Darren Holmes, and today we're going to be using the EMAC Primer Trainer to look at lesson number 8, 16-bit subtraction using 2's complement addition. As you can see, we have 3 totally new instructions that we're going to use today. We have the DAD B, and it has an opcode of 09. Now this is used to add the 16-bit number in the BC register pair to the 16-bit number in the HL register pair and stores the result in the HL register. The carry flag is 1 if the result is too big to fit in the HL register pair. The CMA command complements the bits in the A register, so it changes 1s to 0s and 0s to 1s, and no flags are affected. The INX command increments the value in the BC register pair, and it says that no flags are affected. So, referencing page 748 of the 5th edition of your textbook, you can see we do have the DAD and the add register pair to HL registers. You can think of it as a double add because it's adding 2 registers. So it works on a register pair, so you only state the first part of the register pair, right? It's 1 byte, 3 machine cycles, and 10 T states. So we're going to be working with the BC register pair, so it's just the B, and the hex code for it is 09. Under description it says the 16-bit contents of the specified register pair are added to the contents of the HL register, and the sum is saved in the HL register. The contents of the source register pair are not altered. Page 744 has the CMA command, complement accumulator. And you'll notice that there is only one code for it. It takes 1 byte, 1 machine cycle, and 4 T states. And it says the contents of the accumulator are complemented. So you can't perform this function on any of the other registers. You can only do it with the A register. You'll notice no flags are affected. And they give you an example of before and after. So you can see the most significant bit went from being a 1 to being a 0. And if it was a 0, it has now become a 1. So on page 753, we do have the INX command. It says increment register pair by 1. So you can see it takes 1 byte, 1 machine cycle, and 6 T states. And then you get to decide which of your register pairs you're going to be incrementing by 1. So we're doing the BC register pair, so its opcode is 03. So coming back to the top of the lesson where it gives us new instructions, you need to cross out the 13 and put in 03 because they have made an error here. But you'll notice in the hex code listing for the INX B, they have used 03. So they did correct it in the program listing. They just didn't correct it under new instructions. So you can see here it says the 8085 microprocessor's DAD instruction provides a quicker method of 16-bit addition. It says the following is a simple program that adds the BC register pair to the HL register pair. It says to try running the program with HL equal to 01FF and BC equal to 7001, and it says the result in the HL will be 7200 hex. And you can see it's just one line of code that does all the work for us, so we're not adding high order bits and low order bits. We're just doing a single add. However, the result does end up in the HL register pair. So with the primer trainer on at FF01, I've entered 09, and at FF02, I've entered FF. I'm going to press reset to get me back to FF01. Now I'm going to load my HL register pair, so function HL register needs to be 0, 1, FF, enter. And now I need to load the BC, and it needs to be 7, 0, 0, 1. Press enter. So at FF01, if I press step, now I check my HL register pair because it has the answer. The answer is 7200 as they had predicted. I wonder what's in the AF register pair. So if I press function AF, we can see that none of the flags have been set in this case, and the accumulator wasn't used because it's still 0 from pressing the reset key. So looking at the instructions here, it says there is no instruction for 16-bit subtraction, but this can be simulated by changing the register that you want to subtract to its 2's complement form and then executing a DAD instruction. A number is changed to 2's complement form by complementing every bit and then incrementing the number. So that's why we're going to be using the CMA and the INX commands. Now it says below is the program that subtracts BC from HL by changing BC to its 2's complement form. Then the program adds BC to HL repeatedly. It says note that the result in the carry flag will not indicate a borrow as it did in the sub and SBC instructions. So we have to be careful about that. Now when you take a look at the code, you can see it's going to start at FF01, and the CMA command only complements the A register or the accumulator. So what we need to do is to complement the BC register pairs, we need to put B into A, complement it, and then store it back in B, and then we're going to move C into A, complement it, and store it back in C. Now we're going to increment the BC register pair, and that will make it 2's complement. So that's the INX command. Then we're going to do our DAD B. So that's going to add BC to HL, which is now, because it's a 2's complement number, will actually be a subtraction. And then we've got a new instruction here. Now we have seen it before, but it's the jump instruction, and it jumps to loop. So loop is defined as the DAD instruction. So let's take a look at this JMP instruction. Now we haven't seen the jump instruction for a few lessons now, so it doesn't hurt to go back to page 754 and check out the JMP instruction. It's jump unconditionally, and it's a 16-bit operation, so that's actually an address location, right? So it's 3 bytes, 3 machine cycles, 10 T states, and the hex code for it is C3. So the program sequence is transferred to the memory location specified by the 16-bit address. So this is a 3-byte instruction. The second byte specifies the low order byte, and the third byte specifies the high order byte. So you have to remember it's low order followed by high order. So they've given us the opcodes, and we should always go back and check and make sure that they are the correct opcodes. Now we're going to jump to FF08, and FF08 is the DAD instruction, and we can see the low order byte followed by the high order byte. So we're going to go ahead and type this into our primer trainer. So at FF01 we're going to enter in our program. So we start with F3, increment to F, increment for 7, increment 7, 9, increment 2F, increment 4F, increment 0, 3, increment 0, 9, increment C3, increment 0, 8, increment, and finally FF, increment. So we should be sitting at FF0C right now. So then we're going to decrement backwards just to make sure that we have the right code in there. FF08, C3, 09, 03, 4F, 2F, 79, 47, 2F, and F3. So I'm just going to hit reset to clear all the registers before I move on to the next step. Now they don't break the procedure down into individual steps, but we can do that on our own. It says enter the above program into memory, which we've done. Then we're going to load HL with FFFF and BC with 00FF. Now it says to set a breakpoint at FF08, then run the program. When the program breaks, you will see that the BC, that's a BC register pair, is now the 2's complement of 00FF, which is FF01. Now we're at a single step. The DAD instruction and HL will be FF00. That's equal to FFFF minus FF. So that seems to be pretty simple. Then we're going to single step the jump and DAD again, and the HL will be FE01, which is FF00 minus FF, and so on. With each DAD instruction, 00FF is subtracted from the HL register pair. So reviewing the math, in the HL register pair, we're going to load in FFFF. Then in the BC register pair, we're going to load in 00FF. What we're trying to do is subtract BC from HL. So F minus F will give us 0. F minus F will give us 0. F minus 0 will give us F. And then F minus 0 will give us F. So the result in the HL register should be FF00. Then when we go through the next loop, BC still contains 00FF, so we're going to subtract FF from what was existing in the HL register pair, and that is FF00. Now when you take 0 and subtract F, we have to borrow the 1. In the next column over, it is 0, so that column also has to borrow the 1 from the next column over. So this F becomes E, and we end up with 10 in hexadecimal. Now 1 needs to be borrowed for the next column over, so we end up with an F in the second column. In the first column we have 10, which is 16. So 16 minus F equals 1. And then F minus F equals 0. And then E minus 0 equals E. And F minus 0 equals F. So the result in our HL register should be FE01. So let's check that out in the program now. So with the program loaded into our primer trainer, I'm going to press reset to clear all our registers. Now I need to load the H and L register pair, so function HL. I'm loading it with FFFF, pressing enter. And now I have to load the BC, so function BC register pair, and I'm loading it with 00FF. I'm pressing enter. Now I need to set a breakpoint at FF08, so function breakpoint FF0 and then 8 and press enter. So don't press reset now because it will clear all those registers that you've just entered data into. So now we're going to run the program. So function run, and it stops at FF08. So it says when the program breaks, you will see BC is now the 2's complement. So it's going to be function BC, and it is indeed FF01, which is the 2's complement of 00FF. So press enter so that you get out of the register display. And now at FF08, it wants us to single step the DAD instruction. So press step. So now it's done the DAD instruction, and it says HL will be FF00. So function HL, and you can see it is indeed FF00, which is what you expect FF minus FF to be. Now let's take a look at the AF register pair, and you can see we have 01 in the flag register, and that 1 indicates the carry bit being set. So as they said earlier, you cannot rely on these carry bits when we're doing a subtraction, doing 2's complement. Okay, get out of there. Now it wants us to do a single step for the jump. So C3 is the jump. Single step back to FF08, which leaves us at 09, which is the DAD command. So press step again, and it says HL will be FE01. So function HL, it is indeed FE01. And it says with each DAD instruction, FF will be subtracted from HL. So if I press enter to get us back to the program, do a step over our jump, and then the step for another DAD or another subtraction, I can go function HL, and now you can see my result is FD02. So I just want to refer you back to lesson 6 where we're doing 16-bit subtraction. I did an example showing the low order subtraction where we took the number that we're subtracting and we converted it to its bit pattern. We took the 1's complement of it, then we added 1 to come up with the 2's complement, and then we added it to the other byte, giving us a result, and then the carry bit was actually complemented to come up with our final result for the low order subtraction using the 2's complement addition method that we're doing today. So you notice the carry bit actually has to be complemented, and we did not do that with our 16-bit subtraction using 2's complement addition. So I showed you the CMA or complement accumulator command in your textbook. The next page over, on page 745, there's a CMC complement carry command. You'll notice it has no operand. It's 1 byte, 1 machine cycle, and 4 T-states. Its hex code is 3F. Under description, it says the carry flag is complemented. Under flags, it says the carry flag is modified and no other flags are affected. So we could be using this command to correct our 16-bit subtraction using 2's complement addition. I'll leave that for you to try on your own. So at this point, we've completed the lesson, but I think we'd like to do a second example. So for the second example, I'm going to load HL with FFFF as we did before. but I'm going to load BC with 01 FF. So the result I should see is F minus F is 0, F minus F is 0, F minus 1 is E, and F minus 0 is F. So the result should be FE00 in my HL register pair. So I'm just going to check that again. So going back to my primer trainer, I'm going to load HL with FF, FF, as I did before, and press enter. And then I'm going to load BC, function BC, and this time I want to load in 01 FF and press enter. Now I need to set a breakpoint, so I'm going to go function breakpoint, and this time I'm going to set it at FF09, which is just after the DAD instruction. So FF09, enter. So I'm going to press function run, and now I can check my HL register, function HL, and you can see it's FE00. Whoa, it's FF00. What went wrong? It was the same program. I just loaded different number into the BC register pair to subtract it from HL, and now something's gone wrong. At this point, most students get confused, lost, frustrated, and don't know where to start. So I'm going to show you how to troubleshoot a program so that you will not have the same frustrations as the people sitting beside you. So we tried to run our program with the data from the second example, and it didn't work. So we need to do some troubleshooting, and in programming, troubleshooting is called debugging the program. So it looks like the program's okay. And one of the things that we did was we had to convert from assembler language, which is basically something that we can understand, into machine language, which is something the computer can understand. So to do our debugging or troubleshooting, I like to start by drawing the block diagram of the 8085 CPU. So in there we know we have the AF registers, the BC registers, the HL registers, the stack pointer, and the program counter. So initially when we start up our program, A and F have been reset to 00. B and C we want to load with 01 FF. And H and L we loaded with FF, FF. The stack pointer by default sets to FFD4, and our program counter is looking at FF01, which is the first line of code of our program. Now I recommend you draw these little boxes in pen and then fill them in pencil so that when you go through each step of your program, you can erase the old number and put in the new number. So at FF01, we want to move B into A. So B is 01, and we want to move it into A. So using eraser, you erase the 00 and put in the 01, which is B being moved into A. Now we're going to check that out on the primer trainer. So to start, I press reset. I go function HL, and I load in FF, press enter. Then function BC, I load in 01 FF, press enter. Now at FF01, I want to press the step key. And you'll notice it stopped at FF01. When I press the step button, I don't hear a beep. It doesn't do anything. When I press any of the buttons, nothing is happening. So what's gone wrong? So I'm going to hit the reset button. and that stops whatever's running. And I'm going to try this again. I'm going to go to Function and HL, and I want to put in FFFF, enter. And then I want to go to Function BC, and I want to put in 01FF and press enter. And now instead of doing a single step, I'm going to set a breakpoint. So I'm going to go Function, breakpoint, and my breakpoint's going to be at FF02, and I'll press enter. So now it should stop at the next instruction, or just before it does the next instruction, which is the complement accumulator. So if I go Function run, this time it stopped at FF02. Now I'm going to check my AF register, and you'll notice it's 00. That should be 01. It should have moved B into the A register, but it didn't. So for some reason, when I tried to single step the move B into A instruction, the primer trainer hung up. And then when I put in a breakpoint at FF02, instead of moving B into A contains 00. So my next step is to check this instruction in my textbook to see if there's anything weird going on. So checking out page 757 of my textbook, it's the move instruction, copy from source to destination. I look down here at the table that they gave us. The source is going to be the B register, the destination is the A register, and the opcode is 78. And they've used an opcode of F3. So we have another error in our listing for the program in Lesson 8. So what exactly is F3? So on page 751 of your textbook, hex code F3 is DI, which stands for Disable Interrupts. And it says the interrupt enable flip-flop is reset and all the interrupts except the trap are disabled. So what happens is the primer trainer disables the interrupts. And what's an interrupt? Every time you press a key, that generates an interrupt. So if we've disabled them, our primer trainer just seems to hang up to us. So that's why we have to hit the reset button to get it started again. Now you'll notice it's 1 byte, 1 machine cycle, 4 T states, just like the move instruction. So as far as the processor was concerned, it thought it was running a good program, but now we know we've put the wrong opcode in. So what we need to do is cross out the F3 and put in the 78, and we're going to rerun the program and see if that fixes our problem. So on the primer trainer, I'm going to press the reset button, and then at FF01, I'm going to change the opcode to 78 and press enter. I'm going to go back to FF01. I'm going to load HL, so function HL. I'm going to load it with FFFF, press enter. And then function BC, I'm going to load it with 01FF, press enter. I'm going to set the breakpoint, and I'm going to hope the program's going to work, so I'm going to stop it just at the jump instruction. So that's FF09. And press enter. And then I'm going to press function run, and it stops right at the jump instruction. So my result in the HL register pair, function HL, is now the correct number FE00. Now you're welcome to press reset and go back and try the first number to make sure that everything works on here. So function HL, I'm going to load in FFFF, press enter, then function BC, I'm going to load in 00FF, press enter. I'm going to set my breakpoint, function breakpoint. I might as well stop it at the answer, which is FF 0, 9, enter, function run, check my HL register pair, and it is FF00 as it was before. So with the correction in there, it works for both the original example and example 2. Now this is why you can not only throw one number into a program, you have to try several different numbers to make sure that your program is operating correctly. The only reason it operated correctly for the first example of our program running is because we'd hit the reset button and it had loaded 00 into the A register. It did not move the 00 from the B register to the A register. That's why you have to run several code examples with several sets of data to prove that your program does operate correctly. So let's review lesson number 8, 16-bit subtraction using 2's complement addition, and we're going to be using the Primer simulator. I've gone ahead and loaded the corrected program into memory, so you can see at FF01 I have the correct opcode for move B into A, which is 7-8. So what we need to do is load HL, so function HL, and I'm going to load the HL register pair with F, 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 and press enter. And then I'm going to load the BC register pair with 0, 0, F, F, and press enter. I'm going to set my breakpoint, so function breakpoint, and it's at F, F, 0, 8, press enter. Then I'm going to do a function run, and it says when the program breaks you will see BC, so function BC is now the 2's complement of 00FF, which is FF01. So that's correct. I'm going to single step, so I'll press enter to get me back to FF08. Single step the DAD instruction, which is 09. So step, and it says HL, so function HL will now be FF00, which is FFFF minus FF. So then it says single step the jump, so press enter, and then single step the jump, and we're back to the DAD instruction. So we're going to single step the DAD instruction, and then check HL again, and we can see HL is now FE01 as we had predicted. Now hitting reset, we're going to check and make sure that example 2, which is where we found an error in our code with, right? Always helps to run a second set of data. So function HL, and we're going to load in FFFF and press enter. And then BC, we're going to load in 01 FF and enter. And this time we're going to set the breakpoint at the jump instruction. So function breakpoint, we want it at FF09. Press enter. We press function run. Now we're going to check HL register pair for our answer, and it is indeed FE00. So you can see the importance of running a second set of data just to make sure that your program is running correctly. And if you have a problem with your program, you can use the programming model or the block model of the 8085 and go through each instruction to see what is supposed to happen, and then single step it on the Primer Trainer to see if that is actually what is happening. So hopefully I've shown you in this lesson a little bit of troubleshooting, which in the programming world we call debugging. This concludes lesson number 8, 16-bit subtraction using 2's complement addition. Our next lesson is going to be on binary coded decimal 16-bit addition. So you might want to reference your digital systems textbook, looking up binary codes and the 8421 BCD code.